Hi everyone. So great to be here in this Eindhoven, in Eindhoven with this new PyData. It's great to see that it's coming along so well. So just as a sort of remark for the people who have been at the last PyData Amsterdam meetup, this is going to be basically a recap of what we did there as well. So I won't feel offended if you decide to say, oh, in that case I might want to go to the other talk instead. I see one person leaving. Great. Perfect. So just quick show of hands before we actually get started. Who of you works with machine learning on a, let's say, daily or regular weekly basis? Okay. Who of you put models into production that make decisions about people? That's a couple. Okay. So that's also always something that frightens me. Because if you've been around for quite a while in this field, you've seen models do stupid things. And there's a specific category of doing stupid things, namely when there's unfairness at play, that I think is especially risky and we need to get better at as a field of dealing with. And this image might be familiar. It's been all over the media at some point a couple of years ago. But this is screenshots from a system called Compass. And this system basically tried to assess the rate of reoffenses by convicted criminals. And you can sort of see some odd things on this picture. So basically we compared the two people on the left here and we compared the people on the right here. And this person here who had 2 armed robberies, 1 attempted robbery and a grand theft has a low risk of reoffense. Whereas the person next to him with 4 juvie misdemeanors, just basically boys being boys, has an extremely high risk. And we see something very similar on the right as well. 1 petty theft, like shoplifting, extremely, or medium risk, but domestic violence, aggravated assault, drug trafficking, grand theft, basically a very low risk. And this is kind of scary. And figuring out that your model is doing these kinds of things can be hard, but it can be even harder to figure out what we can do to stop our models from doing this. All the things that I'm going to discuss with you today are implemented already in this library called scikit-lego. You might have heard of it if you went to Vincent's talk earlier today. But it's basically a library containing some of the things me and my colleagues, Vincent, use often in machine learning projects. We basically just bundle them and make them more easily accessible. If you go to the literature and see what people are doing about making models more fair, you sort of see 3 major types of mitigations. These mitigations can be summarized as data debiasing, using fairer models, or post-processing the results of your models. All have their strengths and weaknesses, but if you take a bit of a step back and think about like the packages that we use on a regular basis, in particular scikit-learn, you can see that data debiasing is basically a certain type of transformer. And a fairer model is basically a certain type of predictor that we might want to use. And if we want to do post-processing, then maybe we can use something called meta-estimators to do this. But first, I like woodworking a whole lot, and sort of the main adagio there is always measure before you cut. So let's discuss how we can measure whether our models are doing something that's reasonable or doing something that's unfair. One of the main measures, so we need to be able to measure this. And we need to be able to measure fairness between decisions we make between 2 subgroups, in this case group A and group B. And one of the main measures that you can find is something called demographic parity. What demographic parity says is that the probability of predicting a positive outcome should be equal between the 2 groups. If that's true, then you have complete demographic parity, so a probability of y hat be given that z is 0, where z is a binary sensitive attribute, should be the same as the probability of y hat being 1 given z being equal to 1. So in both groups, we have 4 positive predictions. And on first instinct, this seems fair, right? You have the same amount of people being predicted as positive classes in both groups. There's some issues, though, because what we could have happen is that in our group A, we accept random people, and in our group B, we accept qualified people. This can, in essence, be a good demographic parity classifier, for example. But, I mean, you could argue that it's not fair. And also, if the base rates, like the base rates of y being equal to 1 in our groups are different, this demographic parity measure doesn't allow having a perfect classifier, because it will try to force them to be the same. So instead, something that's a bit nicer to use, I think, is equal opportunity. And this adds basically another condition to our probability, and it says the probability of predicting a 1 for both groups should be the same, given that the true y is also a 1. So given that I am someone who pays back their loan, I have the same chance of being admitted a loan, not dependent on my sensitive attributes. Given that I am someone who is not likely to reoffend, my sensitive attribute does not matter in the decision of whether I'm going to reoffend or not. And that basically looks something like this. So in the dotted line, we have our true positives, and in the black dotted line, we have our predicted positives, and we see that in both groups, 3 out of 5 true positives are predicted as true positives, and therefore, or 2 out of 4 are predicted as true positives, and therefore they are equally opportune. So this is a constraint, in essence. They should be the same. But it's quite easy to turn this into a metric by taking the ratio between them, and that's a number somewhere between 0 and 1, and then you can use it as a metric in whatever you want. So in scikit-learn, let's just try and implement this. In scikit-learn, how do we typically build metrics? Well, we take a function that has y true, y hat, and it gives us back a score. And that's kind of problematic, right? Because we're missing something here. We don't have access to our sensitive attribute. So how are we able to score? Thankfully, there's also something called a scorer. This is a slightly different function, but it takes the classifier, the x and the y, and then as long as our sensitive attribute is in x, then we can use it in our metric to see if our classifier is fair. But I see some of you thinking, wait, sensitive attribute in x? That doesn't sound like a good idea if we want fairness, right? Then we're explicitly telling our model what the sensitive attribute is. And that's correct. But the main sort of trick you need to be aware of here is that this classifier that I've drawn on the screen doesn't have to be a single model. It can be a pipeline. So what if the first step of this pipeline would be to drop our sensitive attribute? The scorer still works on the entire pipeline, so our sensitive attribute is going to be in x, but it's never going to be shown to the actual classifier, which is therefore unaware of it. And then we can sort of have this entire thing working. We can use this for equal opportunity, for demographic parity, or whatever other kind of metric you can use. This is generalizable to maybe consistency over time in time series. There's quite a few cases where you could use something like this. Now that we can measure, we can, so basically, code-wise, it looks something like this. For example, this p% score, that's the demographic parity ratio. Turn it into a function that takes the column of the sensitive attribute that we want to compare our metric on. And then we return a implementation version of that that takes the estimator, the x and the y, and just does the math on the ratios and gives you back the result. In a pipeline, it looks something like this. We start with a column dropper. We do whatever we want in the middle. We can do, I don't know, our categorical encodings and standard scaling and missing values and stuff. And we end with a logistic regression. And if we can put that in a grid search, supply both our accuracy score and our p% score as metric that we want to use, and we can use this to benchmark our models. So what I ended up doing is I put this, the compass data that was subpoenaed at some point inside this logistic regression and posted the results. And what it basically says is it's about 70% accurate in predicting whether someone's going to reoffend. And the equal opportunity score on gender is about 82, and on race about 0.78. So not great, and that's definitely also what was found in subsequent investigations of this. So this is something we call fairness through unawareness. Basically, we just remove the sensitive attributes, we put our blindfolds on and say, yeah, this is fair. And we can quite easily see that it's not the case. And for more complex models, it's going to be even worse. So that brings us to our first mitigation step. And this is a bit of a linear algebra trick. What we're going to try and do is, when we have these two features, feature 1 and feature 2, where feature 1 is our protected sensitive attribute, what we're going to try and do is remove all the information that is joined between feature 1 and feature 2. The idea being that if we can't say anything about our protected attribute based on our other attributes, and we remove our protected attribute from the model, it should not be able to be unfair, because we just removed all the sensitive information from it. And how we implemented this is basically as a modification of the Gram-Schmidt process, which is an orthogonalization process for vector spaces. So we take the projection of feature 2 on our projected feature, and then subtract that projection from feature 2. And that basically means that the features are in the end going to be orthogonal to each other, and therefore should not share any information. And should therefore be more fair. Caveat, it's only linear, right? It's no higher order effects, no interaction effects, so it's definitely not great, but at least it's a try. In code, that looks something like this. So this is going to be a custom transformer in scikit-learn. So we make a class information filter. We inherit nicely from the basis that scikit-learn offers us. And in our initialization function, we basically tell it, this is our sensitive column that we want to filter out from the data set. Inside the fit, we apply this modified Gram-Schmidt process to remove these projections. And we calculate the projection matrix from the unfair representation into the fair representation. We store that so that we can use it in transform then once again to compute from new matrices the more fair version. If we benchmark this, we get quite a reasonable improvement. We see that the accuracy goes down by 1%, but the equal opportunity score on gender and on race goes up quite a lot. Especially because we're using only a simple logistic regression, the linear removal of features, linear fairness debiasing helps here. But it's still not great, and we might want to be able to do better. So what can we do next? Well, we could also say is that we could change our model. In a normal logistic regression, we try to optimize something like this. We maximize the log likelihood of the outcomes given our parameters and our data. But what we actually want to do, if we have such a situation, we want to optimize this likelihood subject to some fairness constraint being higher than a value that we can decide upon. And we've seen some measures of fairness, right? We've seen this demographic parity and this equal opportunity score, which we should be able to basically just plug in here and say that that ratio should be higher than some variable c, higher than 0.9, higher than 0.85. The problem, though, is that when we try to do that, what we'll find out is that these measures are rather unfit for direct optimization. Because they're only dependent on the actual decision and not the decision probabilities, you get quite large saddle points in the optimization process. Also, the constraints themselves are not convex, which makes them just rather hard to optimize in general. So we might need a way in which we can approximate the constraint. It turns out that that is reasonably doable for both demographic parity and equal opportunity by taking the covariance between our sensitive attributes and the distance to the decision boundary for specific observations. So that's basically what we're trying to do here. We take the demeaned sensitive attributes of a user. We take them times, and we take the covariance between this and theta transpose x, so the prediction that we made for the user. And so the average for all the users should be below a certain positive and above a certain negative constraint value. Turns out this is convex, and therefore relatively easily solvable. So then we come to how do we actually solve these convex problems? Well, there's sort of three main approaches. You can use standard solver formulations like LP or QP problems. There's a bunch of off-the-shelf implementations for this. You can basically pip install them and be merry on your way. Something that isn't so nice about them, though, is that these solvers take very specific formats in how they want you to supply the problem. And that format can be quite far away from what you're used to typing if you're just doing math in Python, right? You're used to typing NumPy and basically being flexible in whatever you want to do, and these solvers are not going to just accept that. So what else could we do? Well, roll your own solver, of course. But that doesn't sound great either, right? You kind of want to build on the shoulders of giants and sort of use all the optimizations they made to solve these problems quickly and efficiently. So what I ended up using is use a convex modeling language. And you can sort of see a convex modeling language as a compiler for convex problems, where you plug in a bit of NumPy, or NumPy-like code, and it will decide, based on some heuristics, what the best solver there is that it can use, and how to translate your code into a formulation that that solver will understand. And that sort of has the, for me at least, the best of both worlds. In code, that looks something like this. So this is the solve function from one of these FAIR classifiers, the equal opportunity, the demographic parity classifier, I think. And you can sort of see in the beginning that we're making just a bunch of variables, like the number of observations and features. We define our decision variable, the theta, the parameters of a model that we want to learn. And the next term is basically just the log likelihood of our model given our decision variables. We apply some regularization on that, and then we compute this decision boundary covariance, our constraint, the thing that we want to set a constraint on. And then any API that has a problem.solve is always good in my book, so we basically just call problem.solve on our maximization of log likelihood with our constraints, and we store the coefficients and the intercept on self.coef and self.intercept. This we plug into the rest of a scikit-learn estimator with a fit and a predict. And this basically gives us a nice constrainable classifier. In usage, it looks something like this. We can import an equal opportunity classifier, supply to it which are our sensitive columns and what the threshold of our covariance should be. And if you supply different of these covariance thresholds, you will sort of see that as that covariance threshold gets larger, the fairness of our model will go down and the accuracy will go up. And there's somewhere a trade-off here, and that's up to you to make. It's up to you to decide what you think is a good point here, dependent on your use case and the business you're in. I'm not sure which exact covariance threshold I ended up using here, but we once again see that the accuracy score of our model only went down by a bit. But both the equal opportunity scores have improved by quite a lot. So this tends to work. So, what if we don't have access to our model? Right? Sometimes you end up in a situation where you have a fear that you get a score supplied, maybe from some third party, and you're not sure whether that score is fair or not. And then you're sort of shit out of luck, right? Well, maybe, but maybe you can also do some post-processing. Because if you think about it, if you plot a ROC curve of your model for different thresholds, what you see is the false positive rate and the true positive rate. That's what you get back, right? And we just defined equal opportunity to be a model where the true positive rates of both the groups are the same. So what we normally end up doing for a model is if we plot threshold versus true positive rate, typically we set a certain threshold for both our groups, by default 0.5. But what we could do is basically read from this graph the true positive rate that we want and select two different thresholds for each of our subgroups. Nothing necessarily wrong with it. And then we can basically guarantee that we can have an equally opportune classifier, even though we don't have access to the model itself. In scikit-learn, we have to do this using meta-estimators. And what is a meta-estimator? It's basically a wrapper around an already existing one. So our normal estimators have something like predict, fit, and predict probabilities. And what we'll do is we'll create a class around this that takes one of these estimators and basically shuffles the internals around a bit. So when we call fit, what we're going to do is we're going to basically calculate this ROC curve and decide for each of our subgroups what are the thresholds that we should take to get these true positive rates that we want. And then when we call the predict on the meta-estimator, what we'll actually do is we won't use the original predict of our estimator. We'll use predict proba and compare, like in conjunction with our sensitive attributes and the thresholds that we computed in a fit, we can then give back, should this be a true or a falsely classified instance. Once again in code, equal opportunity classifier. In our initialization, we start with taking a classifier. This is just a base estimator like a logistic regression or a random forest classifier, or whatever you want it to be. And in our fit, we try to fit that. We get the predict probas on that data, and we try to compute the thresholds based on our sensitive attributes and our desired true positive rate. In the predict, we basically just do the regular predict proba of our internal classifier. We use our thresholds, and we say if our y hat is ever bigger than these thresholds for the sensitive attributes, then we treat it as a positive, otherwise as a negative. And I think this is, this implementation was kind of last minute, so this only works on one attribute at a time. So in this case, I just picked the equal opportunity score for gender. I only did it for gender. And we can see that our empirical equal opportunity score for gender is then also very close to 1, which is kind of what we would expect. Of course, it's not a perfect solution. First of all, we need access to our sensitive attributes, right? In all cases, at least during training, but in the post-processing one, even during prediction. And that's going to be a hard story to tell, right? In order to be fair, we need to know your race or your gender. That's going to be a tough battle, but that doesn't mean that it's not a battle that we should try to have at some point. Because not doing anything because we say we don't have we can't use this is probably going to end up being worse. And of course, just because we didn't measure unfairness doesn't mean that we can prove that our models are fair, right? There are other metrics that we can use, and you might want to look into them. Just because your true positive rates is the same, you could still argue that because false positive rates are different, it's unfair in some way because you're allowing more unqualified people of one group to go through than of the other. But still, it's a start. I'm happy to talk to anyone who has ideas about this and to see if we can maybe do something together. But other than that, that was my talk, and I'll gladly take any questions.